All right, so one thing you should know about me is I'm a chemist at heart, but I also really love history. I like learning about the history of science and the history of chemistry. Does anybody know the origins of chemistry, where it came from? Why were people interested in it? Weapons. So that's one reason they were interested in weapons.
They wanted to make gold.
Yeah, they wanted to make gold. So how many of you guys have heard of alchemy? Alchemy is really the origin of chemistry, right? And it makes sense, too, because if you look at the nomenclature, alchemy has chem in it. Does anybody know if we have a way of making gold from non-gold objects? It's kind of a double-edged question. There actually is a way using nuclear chemistry, but it's not practical in any way, shape, or form. Really, alchemy was just this fool's quest of trying to make a new element from other elements. It didn't work very well, but the good thing is, in that process, we actually discovered a lot of really cool stuff, from medicine to understanding how biology works, to understanding how geology works, building new electronic devices, meteorology, making new metals, engineering, ecology, archaeology, agriculture, botany, biology, biochemistry, pharmacology, you name it. Chemistry is pretty much involved in it. It's one of those things where I remember when I was taking science classes, my teacher told me biology is really chemistry, chemistry is really physics, and physics is really math. Have you guys heard that? Everything's really tied together. My advisor in grad school told me, you are not a chemist, you are a scientist. And I think that's really important to remember, is that as a scientist, you have to wear multiple hats. You have to be capable of adapting to a lot of different situations in order to solve problems. So let's talk a little bit about the scientific process. How many of you guys are familiar with this? Most of you? This is something that's normally taught in high school or middle school. And it's a really easy, intuitive thing for us, but it's important that we follow it pretty rigorously. So the first step in the scientific process is you observe something, right? So the first step's always this observation step. Typically, you want the observation to be something that somebody else can observe too. So for example, if I see imaginary creatures flying around me, that's not a great observation unless somebody else can see them too. So the observations need to be repeatable. And then from this observation, you normally derive some sort of question. A question related to that observation. So for example, why are the flowers blooming in spring? Would be a good question. What happens after you develop a question? Does anybody know? Close. So you make an experiment at one point in the scientific process, but typically you have to develop something that starts with an H. Does anybody remember that word? Hypothesis, right? So experiments are incredibly important. However, in order to really have a well-controlled experiment, you typically have some sort of testable hypothesis. That's a really important feature. And the key word here is testable. A lot of people get the term hypothesis confused with a question. A hypothesis is something that you can test clearly to get an answer out of it. A question is just a question, right? At this point, you want to test the hypothesis. And this is your experiment. The reality is that being a scientist, this rarely ever goes smoothly. Almost every time you run an experiment as a research scientist, it doesn't go according to plan. But that's okay, because ultimately, this is kind of this loop cycle, where if things didn't work out the way that you had planned, you can reformulate your test and rerun your experiment, right? So oftentimes you're stuck in this loop for a while of testing your hypothesis, coming up with a new hypothesis, testing that new hypothesis, and then so on and so on. After this, you can collect a bunch of data and you can develop something called a theory. A theory explains what happened in that situation. A theory is a really, really good explanation because it's supported by all of the data that you've gathered through all of your experiments. The other thing, too, is that oftentimes you're not done. I don't like how they show the scientific process in a lot of textbooks. They show it as this linear sequence where it's just like you have a start and an end. The reality is oftentimes this theory leads to a new observation or a new question, and then you're stuck in a new cycle, and then you branch out into a completely different field. So this isn't a static thing. It's a very malleable thing. It's something that's used in basically every single scientific discipline. Are there any questions with this? All right, so let's define some of these words in a little bit more detail. I'm going to be using a lot of terminology. If I'm ever using terms that you don't recognize, let me know and I'll write the definition down. The first one that we already mentioned was our hypothesis. And a hypothesis I like to describe as an educated, testable guess. Whoop. So for example, your question might be, why are flowers blooming right now? Your hypothesis could be, well, daylight's getting longer. Maybe my hypothesis is that plants start to bloom as soon as daylight gets to a certain amount of time, right? So you could come up with something that you could test in a greenhouse where you put a lamp above your flowers, you change the amount of time that that lamp's on, and then see whether or not your flowers bloom. Something like that would be a hypothesis. The key thing is you want it to be educated. You don't want to waste your time doing silly things like saying, all right, my hypothesis is that flowers bloom because I turned 31. Doesn't make a lot of sense. It doesn't conform with most of your scientific knowledge. Try to always use an educated hypothesis. Theories are the things that are developed after you've run a bunch of experiments. And we said that this is an explanation. That is supported by data. One thing I really don't like on the news is people will say, well, that's just a theory. But that doesn't make any sense. You're saying that's just supported by data. It's not a good way of trying to refute somebody's argument by calling it a theory. A theory is something that's really sound because you've got a lot of data backing it up, right? So whether or not you hear it in regards to climate change, oftentimes I hear that all the time where they're like, it's just a theory. And it's like, well, we've got a lot of data supporting this theory. You can't use that as an argument against something, right? The next thing we have are scientific laws. Does anybody know how a law and a theory differ?
The law cannot be proven wrong. It can't be, it's like that.
Yeah. A law is cut and dry, right? Oftentimes laws are presented as basically mathematical formulas, right? So if you've taken any physics, you've probably been given formulas for like Newton's laws. Those are things that are often represented with a mathematical formula. It doesn't explain how it works, though. It's just the nuts and bolts. So it's a summary of a large body of information, but provides no explanation. So the key thing is that a theory provides an explanation that's backed up with data, where a law really doesn't. It's oftentimes just a math formula. Does that make sense? We're going to be using these terms a lot, and it's important that we get these squared away. We are going to finish up today's lecture. I think we still have time. Yeah, we've got 10 minutes. Talking about how do we convincingly share or explain theories. This is a big problem, especially in today's society. I feel like more and more people are becoming increasingly skeptical of scientists and the data that they provide. And it's important that we convey information in a way that people believe us and that they trust the way that we're doing science, right? So the way I like to do this is the method that's presented in your book called flares. And this is an acronym. The F for flares is falsifiability. Basically, there must be a way to prove your experiment as incorrect. So there must be a conceivable way to prove your claim false. So for example, if you design an experiment where you can get nothing but positive results, that's a crumbing experiment, right? You need to design an experiment where there's at least the potential of getting a negative result. The other important thing to come out of this is that you can never prove something to be correct. You can only prove something to be incorrect, right? So scientists can't prove something, but we can provide overwhelming evidence. The only time you can prove something is in math, right? In math, you can do proofs. Scientists, we don't have that method. We can provide overwhelming evidence in support of something, but we can't provide absolute 100% truth. All right, the next thing, too, is the L, which stands for logic. We must use logical reasoning as the foundation of everything that we do, right? Science is very weird this way in that we really try to stay out of the realm of the spiritual and the supernatural and all of that stuff. We want to be provided experiments that we can explain using evidence and data. Anytime you're explaining something that can't be explained using data or be tested experimentally, that's when you're dealing with like philosophy or the spiritual or stuff like that. We don't even try to get into that area because that gets really muddy really quick. The next thing is R, which is reproducibility. It must be reproducible. So for example, if I go buy a lotto ticket and I win, I can't say every time I buy lotto tickets I'm going to win, right? That's not a reproducible experiment in any way, shape, or form. So anytime you have an experiment, oftentimes you do it multiple times, even if it did exactly what you thought, just to confirm that what you saw happen is correct. And then the last one is my favorite. This is sufficiency. The evidence you collect must be adequate. This is my ultimate pet peeve one, and I think it's the pet peeve of most scientists, is you'll see some grandiose claim made, but they really didn't do their due diligence when collecting all of their data. They just got one good data point, and then they ran to the media and they said, look at what I found. I cured cancer with this new snake oil. And it's like, no, maybe you didn't. So you have to have sufficient evidence anytime you're making some sort of claim. And so let me clarify this with a few more points. Scientists always have this burden of proof. And I'm going to put proof in quotes. Like I said, you can't prove something, but you have the burden of providing overwhelming evidence supporting your claim, right? You can't just trust people off of a little bit of details. The next one is that extraordinary claims require extraordinary evidence. So this comes up over and over in science. Oftentimes you run into these claims that are just over the top. The classic example was in the early 1990s. These chemists went in front of the press and they said, we've discovered a way to produce unlimited clean renewable energy through this process called cold fusion. Does anybody remember that, or has anybody heard about that? Fusion is a process where you basically take two atoms and you smush them together. And when you do that, you release an incredible amount of energy. It's basically the reverse of an atomic bomb, and it's what powers all of our stars. The problem is no scientist in the world had ever been able to replicate what they were doing. And they went out and they made this extraordinary claim, but they didn't have the evidence to back it up. Ultimately, it became this giant nightmare for them because then they had to basically backtrack, and now they're kind of blacklisted within the community. Anytime you're making an extraordinary claim, you've got to have a ton of data to back it up. The next one that is a big deal right now is correlation is not causation. And I'll show you guys my favorite chart that explains this, I think, pretty clearly. Oh, no. Oh, did I delete it? Shoot. So this chart, I'll just draw it. Basically says, all right, if we track time on this axis, and we track cases or number on our y-axis, you can plot time from about 1980 to 2017. And one of these, what they did was they plotted the sales of organic foods. And in 1980, not a lot of people knew very much about organic food, so it was pretty low. And then they kept on seeing it climb all the way up to today's amount, right? And they said, wow, this has a pretty nice curve following it. And then another group said, all right, let's track the cases of autism. In 1980, autism wasn't well diagnosed. So a lot of people were just called different or were left undiagnosed, and they tracked this through time. And voila, all of a sudden you've got two correlated lines, right? Does that mean that organic food causes autism? No, not at all. There's actually, Google Analytics has this thing where you can find all these goofy correlations where it's like amount of people drowning in a bathtub versus the number of blockbuster movies in a year. It's just goofy stuff like that. Correlation is not causation, but people are very, very tempted to try to link things together. The only way you can convincingly link things together is to run an experiment showing that they are linked, right? So this is a really big deal. All right, the next one is that authority isn't evidence. Just because somebody's famous or well-known doesn't mean they know more than you, right? They still have that burden of being a scientist. This is a big deal, especially when people are making claims well outside of their area of expertise. So for example, if I made some elaborate claim about, I don't know, let's say immunology. I don't know very much about immunology. I wouldn't trust me. You shouldn't trust me either. So what you should do is be skeptical of everybody and everything and rely on their data. Try to ignore their name and just look at their experiments. It's a really good strategy, and it's becoming somewhat of a problem. Scientists and the media are really latching on to this idea of superstars, right? It's fun to read about people in the newspaper and follow all of their science, but you still need to look at the underlying data that they're presenting you with, right? It's a big deal. Has anybody heard of the blogger, The Food Babe? She's one of my worst nightmares. She's one of those bloggers you always see posted on Facebook where it's like, did you know that if you drink club soda, you could die of cancer in 12 years? And it's like, oh my gosh. There's a lot of that going on in Facebook, and you need to be incredibly skeptical. Just because somebody has a blog or just because somebody got their little blurb on the internet doesn't mean that they know what they're doing. There's a lot of that going on right now. I'm sure you guys are aware. Are there any questions so far? All right, so I think what we'll do is we'll kind of stop right there. Tomorrow what we'll do is we'll talk about physical properties, and then we'll talk about physical versus chemical change. If you're on the wait list, come up and talk to me, and we can figure something out.